Hi everyone, I am Hina Wajid and I have passed my ARDMS exam with 94% marks in SPI and 94% marks in OBGYN. Now here on YouTube, I share SPI related MCQs and tips to help others pass ARDMS exam too. If you want full SPI session and all topics explanation according to ARDMS content outline and their syllabus, then you can find the link in the comments to check some of the free PDFs, some of the free videos, and you will also find details how to contact us to join our complete session. First, some questions from the last discussion. So, this means, what is the cause of the color bleeding artifact? Main cause.
Color bleeding artifact is the gain.
Yes, high gain. So, high gain is a main cause of color bleeding artifact. So, what we can do to reduce it?
Increase the gain.
Cause is increase gain. Now we want to reduce it. So,
Reduce the gain. Reduce here.
lower the gain.
Lower the gain.
Lower the gain, okay? Cause of bleeding is high gain. So to correct it, we have to lower the gain.
Lower the gain here.
Okay. What is the solution for the wall thumb artifact?
Wall thumb artifact is the wall filter.
Yes, we will increase the wall filter to reduce the wall thumb artifact. Okay. To reduce the aliasing, we have to increase the depth or we have to reduce the depth?
We have to reduce that.
Yes, we have to reduce the depth.
Yes.
Okay, good. Now, these topics we have already covered in the Doppler, CW Doppler and pulse wave Doppler. And now because we are doing again the basics. So, these topics are again there. And there is a little bit more detail. All other details are same. So, this means what is the difference between CW Doppler and PW Doppler?
Right. So basically, CW is continuous. All right. So there will always be transmission of sound and a receival. All right. So basically, there is two crystals. One will be transmitting crystal, one will be receiving crystal. All right. And because of the very high velocity, is basically used for Doppler studies like to check for cardiac and all. Okay. And it doesn't have 2D imaging. Okay. So you can't tell where the echo came from. It has no range resolution. We have no idea where the signals is coming from.
Okay, and what happens in pulse wave Doppler?
Okay, so in pulse wave Doppler, we basically have so basically transmitting, we wait and then we receive. Okay, so there's only one crystal there. There's transmit and receive. All right. So sample volume will be done in the middle of the vessels. Okay, so basically, pulse wave tells us more about the blood flow. Okay, the detection of Doppler shift lah.
Okay, so CW Doppler is like you keep a flashlight on all the time and it keeps shining without blinking. That's exactly how a CW ultrasound works. The transducer keeps sending sound waves non-stop. It never takes a rest. But since it's sending sound continuously, it also needs to listen continuously. That's why it have two separate crystals. One crystal transmits sound all the time and the other crystal listens all the time. Yes. So CW Doppler is perfect where there is a very fast moving blood through a heart valve or vessel. Why? Because Jasmine, why?
Sorry, wait.
It is perfect for the fast moving blood, for the very high velocity blood, especially through a heart valve or a vessel where blood.
Because there's no aliasing.
Because there is no aliasing, because there is no off time. Because there is no off time, you never miss a movement. And there is no Nyquist limit. Because there is no off time, there is no Nyquist limit, there is no aliasing. And because it's always listening along the entire path, it covers the full path. It does not know where the sound is actually coming from. So range resolution of the CW Doppler is good or bad?
Bad.
Bad, yes. It can tell you how fast the blood is moving, but not at which depth that flow exists. So that's known as having no range resolution. So you can think of it like standing in a hallway and hearing someone clap. You know someone made the sound, but you don't know how far away they are. So CW Doppler listens the sound and listens very high velocity sound, but it can't tell from where it is coming. So that's CW Doppler. No aliasing, high velocity measurement are obtained, but no depth information, no range resolution. So CW Doppler transmits and receives continuously because there are two crystals. One sends, other transmit. One sends or transmits, other receives or listens. So one crystal transmits, other crystal receives, and it obtains information from all the path, from all of the vessels. So it does not tell us exactly from where the signal is coming from. So what are the key points this mean?
Okay, so basically there's two crystals. Alright, one be transmitting crystal, one will be receiving crystal. Okay, so basically because of this, okay, as it's continuously receiving and sending sound, the duty factor is 100% on, or we call it 1. Alright, now it measures high velocity without aliasing. Okay, but there is no range resolution. We have no idea where the signals are coming from, no depth information.
Excellent. So it have two crystals, one transmits and other receives the signal. So imagine two friends. So one keeps talking non-stop, that's the transmitter, other keeps listening, the receiver. It has two crystals. One continuously listens, other continuously transmit. So one is continuously transmitting, other is continuously receiving. There is no break. And they never exchange their roles. One is always listening, other one is always transmitting. So that's happen in CW Doppler. And you can listen very high velocity blood flow signal, but the problem is you don't know where it is coming from. Now here is a comparison. So there is a CW feature tables. We can see it has two crystals and beam is continuous because continuous transmission, no gap. Duty factor is 100% because it is always on. There is no range resolution used in cardiac and vascular studies where blood velocity is very high. Advantage is meeting high velocities. Limitation cannot determine depth of signal, and it is very important topic. So CW requires how many crystals? two. One to transmit, one to receive. Now about pulse wave Doppler. So how many crystals it have, Tesween?
There is only one crystal. It transmits, it waits, and then it receives back the echo.
Yes, there is only one crystal. It first transmits and then it only receives. It only do one task at one time. So it's like imagine clapping once, waiting for the echo and then clapping again. That's PW ultrasound. Same crystal do both tasks. It transmits, then take a pause and then it only receives. So there is a delay in the transmission. And PW is the basis of all imaging systems and most Doppler modes. Like usually we perform pulse wave Doppler routinely to check blood vessels, to check blood flow in the organs like kidney, liver. So routinely pulse wave Doppler is used, and when there is very high velocity blood flow, then CW is used. So here we can see the pulse wave Doppler. First it transmits and then it receives. One task at one time. So what about range resolution of pulse wave Doppler? This means
There is range resolution.
there is
Range resolution.
there is good range resolution.
Yes.
Because there are sample gates that open at a specific time when the echo is coming from a specific point. It ignores all other information. Its receiver ignore all other information. Focus only on the echoes where our sample gate is placed. So because there is a sample gate, so there is a good range resolution. So what's the benefit of it?
So basically, since the pulse is sent out and then pulse wave actually waits for the echo, we are aware exactly how long does it take for each echo to return. Okay, and then the depth is calculated using the range equation, where distance is equals to speed times time divided by 2, because it goes and comes. All right, so being that we are aware there's excellent range resolution, okay, because of the receiver processes the Doppler shift when the gate is open. So it opens and closes at a very specific time.
Okay, good. So because the same crystal send out first pulse of the sound, quickly switch to listening mode to catch the echoes before sending the next pulse. This allows it to know exactly how long it took for an echo to return. And therefore, it can calculate the depth of the structure because it knows the time. It knows the time. So that's why we can calculate the exact depth of the structure. Distance is equal to speed multiplied time divided by 2. This is also known as range equation. And why divided by 2?
Because it goes and comes. We only want to measure one.
Because it goes and then comes. But we need only the time when it comes back. So we divide it simply by 2. So that's how we can calculate the depth, and we say its range resolution is excellent because it has the ability to know where the echo actually came from. Now here's a comparison between CW versus PW. Tesween, please repeat it.
All right. So transmission for CW is continuous. It has 2 crystals, receiving and a transmitting crystals. The duty factor is 1 because it's always on. Okay. So basically, since there is no depth, there is no range resolution. All right, and it measures very high velocity. It only uses Doppler. There is no 2D imaging. Whereas for the pulse wave, there's only one crystal where the crystal actually sends the pulse, waits, and then receives back the pulse. So this makes actually the duty factor less than 1. Okay, but due to the depth, we are aware of where the range resolution or from which distance, which depth that the pulse is, the echoes are returning from. Okay, velocity limit is limited because there is a chance of aliasing to occur, and pulse wave uses 2D imaging and Doppler as well.
Okay, very good. So again here we can see the comparison. Continuous wave Doppler transmission reception happen at same time. Pulse wave Doppler only one crystal. First it transmits, then only receives. So again here we can see in pulse wave Doppler, pulse transmission, a break. In that break there is only listening. Then transmission, break. Then transmission. CW, continuous transmission. And continuous receiving of the echoes, continuous reception. So pulse wave transducer use how many crystals? Only one. It sends and receives both. Okay, now next topic is pulse repetition frequency. This means, what is the PRF?
Okay, so it's basically the number of pulses that we send per second.
Yes, number of pulses sent per second. Now, what is the unit of PRF?
PRF is basically in kilohertz.
Yes, commonly in kilohertz, but we can say its unit is hertz and kilohertz both, because PRF, pulse repetition frequency. So its units are both hertz and also the kilohertz, and typical value is 1 to 10 kilohertz. So we commonly use kilohertz, but hertz or kilohertz both. And what thing controls the PRF?
The pulsar.
Yes,
Pulsar controls the PRF.
the pulsar, because it provides the voltage to the crystal. Also there is like a clock in the pulsar which decides the timing and number of pulses transmitted per second. We will discuss these things in detail later. The functions of all of the components of the transducer, which includes the pulsar as well. So this line is important, that who controls the PRF? So pulsar controls the PRF, and also depth of the field influence it. If there is increased depth, this means PRF increases or decreases?
Increase the PRF reduces.
Increased depth, PRF reduces because it takes more time. So PRF decreases when depth increases, and when depth is less. Superficial structures. For superficial structures, PRF is high or less? High, because pulse goes fast, comes back fast, so there is a higher PRF. So PRF is inversely related to depth. More depth, PRF decreases. So here we can see the special pulse length. What is the special pulse length?
The special pulse length is actually the one pulse.
Total length of one pulse is the special pulse length. So its number of cycles, how many cycles are there, multiply the wavelength. That is the formula for the special pulse length. Okay, this means, what is the relationship between axial resolution and special pulse length?
It's half. Um, it's half SPL. Axial resolution is half of the SPL.
Axial
Better
resolution
axial
is equal to
resolution.
SPL divided by 2 half SPL. Okay. So what happens if SPL is reduced? More axial resolution or less?
SPL
Like better
is
axial resolution or worse?
is shorter SPL, better resolution.
Okay, good. Shorter SPL means better resolution. And increased SPL mean resolution
Reduced.
will be reduced. Okay, good. What happens if there is more damping? So what happens with the SPL?
More damping than good, better, shorter SPL.
Yes, more damping means shorter SPL. It's like a DJ telling the crystal, stop now. So, more damping, shorter SPL. Pulse repetition frequency is number of pulses transmitted per second. So, if time is 1 second and there are 3 pulses, so what is the PRF?
V.
Yes. So, there is 3 pulses. Number of pulses transmitted per second. So, PRF will be 3 here. If depth is more, PRF is reduced. And if velocity is high, so then PRF is also high. So there is an easy example to understand this PRF concept. Think of throwing a ball and waiting for it to bounce back before throwing again. If the wall is close, so quickly ball will go and return. So there is high PRF. If the wall is away, you have to wait longer to again catch the ball and throw the ball. So it means low PRF. So same. If depth is less, PRF is high. If depth is more, PRF is less. So that's how the ultrasound system avoids sending a new pulse before old echoes return. What happens? First, there is a transmission of pulse. So system waits for echoes to come back and then it sends a new pulse and then again it waits for the echoes to come back. So this happens in pulse Doppler ultrasound. So if depth is 5 cm and PRF is 10 kHz, when we double the depth 10 cm, what happens with the PRF? Tasween?
It reduces by half.
Yes, it reduces by half. And when we further increases from 10 to 20, then what happens with the PRF?
The time to 20 doubles. PRF again will be reduced by half.
Exactly. So it again reduces almost half. So first 5, then it becomes 2.5 kilohertz. So double the depth and PRF becomes half. So they are inversely related. So what happens when imaging depth increases? PRF?
Reduces.
Yes. Then PRF reduces. Okay, now next one is pulse repetition period. So pulse repetition period, it's like the time from start of one pulse to the start of the next. So we can say it's total time one pulse takes to transmission and then again reception. Time of one pulse is a pulse repetition period. So what happens when the PRF is high? PRF high, PRP is increase or decrease?
Decrease.
Inversely related. When pulse repetition frequency increases, more number of cycles per second, the time between them is reduced. Pulse repetition period decreases. And okay, I will draw it here. So if 1 second time and there is only 1 cycle here, but now here we have 3 cycle in 1 second time. So now this one cycle, it have more time, right? And here, because there are more number of cycles, I draw cycles here, but like you can assume the full pulses. What is pulse? Like there are multiple cycles, then we say it a pulse. So okay, let me draw pulse here now. Okay, 2 pulses in 1 second. And the first cycle concept which I draw is simple frequency and period concept. But now here we discuss the pulse concept. So pulse is a group of many cycles. Now there is one total pulse in 1 second, and here there are 2 pulses in 1 second. So we can see this pulse have like more time now. All 1 second time go to this one pulse, and here 2 pulses. So 1 second time has been divided between these two. Both get only 0.5 second time. So when there are more number of pulses, the time of one total time one pulse take is reduced. We can define as time one pulse takes, or we can say the time from start of the one pulse to the start of next pulse, or the total time one pulse takes. Both are the definition of pulse repetition period. And when more number of pulses, the time between them is obviously reduced. When less number of pulses, the time one pulse gets increases. And it is measured in time units, in second, and commonly millisecond or microsecond. It includes both the on time, the pulse duration, and then the break, the listening time or the sound off time, both. And pulse repetition period is 1 divided by pulse repetition frequency. These are inversely related with each other. So here we can see different pulses. Okay, here we can see wavelength from one point of cycle to the other. And what is a spatial pulse? The whole distance of one pulse. Wavelength is related with the cycle, one cycle. So this cycle length is the wavelength. And what is the spatial pulse length? This whole pulse length is the spatial pulse length. So wavelength related with one cycle. As you can see here, spatial pulse length of the whole pulse. There's a difference between them. Pulse repetition period, time taken by one pulse. And what is simple period? Time taken by one cycle. Period, one cycle time, and pulse repetition period, it's a time taken by one complete pulse. So it includes both on time, transmission time, and reception time too. And pulse repetition period and pulse repetition frequency, they are inversely related with each other, and its unit is in the seconds. Okay, this means When there is increased depth, what happens with the pulse repetition period? Increases or decreases?
Increase depth, meaning it's going to pulse is going to be sent, and then there'll be a listening time for the echo to return. So there'll be less PRF. Okay, so since PRF and PRP is inversely related, so the PRP is going to be longer.
Exactly. Now pulse repetition period is longer because pulse takes more time to come and go back. So it's that time. So there is more time. What about frame rate? Increases or decreases?
For lower for more deeper frame rate reduces.
Yes, because it's taking more time. So less information is gathered. So frame rate is reduced. Less number of images displayed per second. Shallow depth, it means high PRF, and time pulse travels and comeback is reduced, shorter PRP, and frame rate is good. For the shallow depth, temporal resolution is good or bad?
Shallow temporal resolution is good.
Yes, because frame rate is high. So modern systems automatically adjust PRF when you change the depth. So here we can see pulse repetition period. First, pulse transmission, then there is a pause. So there is a pulse repetition period time. Pulse repetition frequency, total number of pulses transmitted per second, is the PRF. So if PRF is 2000 Hz, what about pulse repetition period?
It's 1/2000.
Yes, so answer is 0.0005 or 0.5 millisecond. PRF is 4000, so 1 divided by 4000. So it becomes 0.25 millisecond. So higher PRF means shorter PRP.